Okay, so welcome back. So today, last time we started on inner product spaces. We saw the Gram-Schmidt orthogonalization, and I omitted the proof, but basically there was some algorithm, and then we defined the ortho-complement or the orthogonal complement to any subset of an inner product space over, as usual, F is R or C. So F is R or C. This is always true. Global disclaimer for the rest of this course, which is just like 2 or 3 more lectures. Anyway, so the point is the ortho-complement is a subspace for any subset S, and moreover, it satisfies some basic properties. This is the main result that we will be using, I think, to define projection operators. So yeah, so let's suppose S is any subset such that the span of S is finite dimensional. Then the vector space is the direct sum of the span of S, that subspace, and the ortho-complement. And notice that here I don't need the vector space to be finite dimensional, just the span of S. So another way to say it is if you have any finite dimensional subspace W, I could take S equals W itself. Then V equals W plus W complement. So let me maybe write down the corollary before writing down the proof, but it's basically the same result. So corollary, or if and only if, rather, if W contained in V are vector spaces, are A, well, that's in fact better. If W contained in V together with an inner product, and dimension W is finite, then V equals W plus W perp. Okay, so that is the claim. So let's start proving it, and everything else. Okay, fine. Right. So first of all, we can say that since S itself spans its span, S contains a basis of the spanning set, and since the span is finite dimensional, S contains a finite basis. So proof of theorem, proof of proposition. I mean, the corollary is just set S equals W. And you get the corollary for free, and because then W is its own span. But now I'm going to prove the proposition. So prove proposition. So since S contains a basis, of the spanning set, of its span, sorry. And let's give this a basis of names. Let's say S1, S2, SK maybe, or what have I written? Yeah. Actually, maybe I should first have said maybe this is part B. Part A. Part A is that if S is the empty set, or if the span of S is 0, then this is obvious. V is 0 direct sum V. So S is contained in 0. So okay. Otherwise, so if S is contained in the origin, meaning S is either empty or the origin, then the result is trivial. This is visible. Otherwise, S contains a basis of span of S, and here because the span of S is not just the 0-dimensional space, here I can assume that K is bigger equals 1. Yes. So now because K is bigger equals 1, I can apply Gram-Schmidt. Hence by Gram-Schmidt. Let us write down a basis V1, V2, Vk, which is orthogonal of span. So there exists an orthogonal basis. Right? V1, V2, Vk. Right? So you just convert the original basis, take any spanning set, take a basis inside it, such a basis exists. I don't care what that basis is. But now, from that basis, I can construct an orthogonal basis of span of S. And I don't really care about the basis one at a time, I just care about the basis together. Now, once I have this basis, I can now start defining. So now the idea is, what do we have to do? We have to say every vector can be written as something in the span of S, there's something in S perp. So let's start with it. Okay. So now let's see. Okay, and also I want to show the uniqueness part, right? So which one should I do first? Uniqueness part just says that Okay. Okay, let's do it step by step. So first of all, I want to show every vector breaks up into something here and something here. So given V, define Vs to be summation I goes from 1 to k V I comma V divided by Vi comma Vi. Remember, these guys are an orthogonal set and they are linearly independent. So none of these Vi's are zeros. The denominator is strictly positive. And so I can do this. Okay? I'm defining Vs to be this thing and I'm defining V_perp to be V minus Vs. Okay. Very simple. I'm defining two different vectors. One is this vector here and one is just this vector. Now, of course, the claim is, so clearly, if you add these two vectors up, you just get V. And so I'm going to claim that Vs belongs to here and V_perp belongs to here. So certainly every single vector can be written in this way. So indeed, at least the sum of these two subspaces is V. And then you have to show that the sum is direct as well. Okay, so let's do this. Okay, this eraser is slowly dying. Anyway, fine. So, given V and V, define this thing. Okay, so clearly this is in the span of S because all of these VIs are a basis of this span. So they belong to this span in particular. So the linear combinations belong to this span. So this guy is clearly in the span of S. The claim is that V_perp belongs to S_perp. So clearly Vs is belongs to the span of S. That is obvious because the VIs are in the span of S. So now why is V_perp? The claim is that V_perp belongs to a So how do you show that something is perpendicular to every vector in S? Okay, so in fact we show, so in fact we came that V_perp is orthogonal to a bigger set than S. So right, so it's not just orthogonal to S, which is the definition of S_perp, it's orthogonal to the span of S. Okay, so this the point is that these two statements are equivalent. To say that something is perpendicular to S is the same as saying it's perpendicular to the span of S, because perpendicularity or orthogonality is a linear relation. So if something is perpendicular to two vectors, it's perpendicular to their linear combinations as well. Right? So that's why this is true. But in fact, for the same reason, instead of the span of S, it's enough to prove that it's perpendicular to all the basis elements V1, V2, Vk. Because if it is perpendicular to all the Vi, then it's perpendicular to all linear combinations, and therefore, so since orthogonality is a linear relation, this is a very imprecise statement, so I'll just put it in quotes. It suffices to prove, it is enough to show. So I want to show that this thing is true. To show this, it's enough to show that V_perp is perpendicular to any basis of span S, in particular to this orthogonal basis. It's enough to show V_perp is perpendicular to Vi for all I. Let's say Vj for all j. So j less equals k. Let's calculate. So compute. We compute, so let's do V_perp comma V. let's do Vk comma V-perp, Vj comma V-perp. I mean, so if I did it the other way, I would have to take a conjugate, but that's the same thing. This is Vj comma V minus summation. So it's minus Vj comma, okay, minus Vj comma Vs. Let me just say that first. But Vs is a linear combination, and the inner products are, of course, linear in the second coordinate. So this is Vj comma V minus summation I goes from 1 to k. Vj, sorry, so first let's write down the coefficient Vi comma V over Vi Vi. Sorry, and then there was the Vi here, but all this is in the second argument. This is Vj comma Vi. And now we remember the fact that the Vi's are orthogonal. So this is always 0 except for the term I equals j, in which case it's Vj. And so we write this down, Vj minus. So basically this is the same calculation you have seen before, and I'm doing this again. So now only the I equals j term remains. That means I have to put j everywhere. Okay, and then this becomes again also Vj. And now these inner products cancel, those two terms cancel, and you get 0. And so it's enough to show that this is true for all j, and that's exactly what we have shown. Okay, sorry, so I'll just say this much. So first of all, so what we have indeed shown is that this sum, that V equals the sum. This shows that V equals the span of S plus S-perp. And now we need to show that the sum is direct. Okay. So how do you show sum is direct? Suppose V equals Vs plus V-perp, and then also V prime S plus V prime perp. How do you show that Vs equals V prime S and V-perp equals V prime S perp? Okay, so this is part D, and then part E finally. We claim that the sum is direct, and that's the same as saying that the intersection is 0. Why is that the same? Because say V equals Vs plus V-perp, right, is also equal to, let's say, V prime S plus V prime perp, whatever that means. Let's call it Ws plus W-perp, so I don't have to write primes. Yeah. In that case, what happens? In that case, if these two are equal, then I can subtract Ws here and subtract V-perp here. Then what we will get is Vs minus Ws is equal to W-perp minus V-perp. But notice the left hand side belongs to, well, this is a subspace, so the left hand side belongs to span of S, and the right hand side belongs to S-perp. So these are two different subspaces, and so you get that something in this subspace equals something else in this subspace. What do we want to prove? We want to prove that Vs equals Ws and V-perp equals W-perp. So you want to prove that this equals 0 and this equals 0. So if you can prove that the only point common to both the subspaces, right, so this is whatever point this belongs to both span of S and it belongs to S-perp. So if you can show that the only point common to both of these subspaces is the origin, then you have already shown that this must be equal to this and this is equal to this. And so in fact they're equivalent. So it's enough to show this thing. So let us show this. Yeah, so the final claim is that the intersection of these two elements is 0. These two spaces is 0. Okay, so the claim span of S intersect S perp is 0. And the proof is very easy. How do you prove it? You can try to prove it yourself. So you can pause the video for a couple of seconds. Okay, but for those of you who just want to enjoy the show, here is the. Well, in this case, this one I can genuinely say is super easy, barely an inconvenience. So let's see, what is this? This one is straightforward. Right? So take any element which is common. So that means first of all, it's so say V belongs to this intersection, span of S intersect S per. Because V is in the span of S, V must be a linear combination. And in fact, we not only that, we know what it is. We know that the linear combination is V, whatever that thing was, summation Vi comma V over Vi. I think we proved this last time. Right? If you have anything in the combination in the span of an orthogonal set, then those coefficients are uniquely recoverable. V equals this thing, Vi, and this is orthogonal to Vj for all j. But what does that mean? If you take the inner product, which we just did, what you get is when you take the inner product, all the terms except the jth term vanish, and the jth term becomes Vj comma V, where Vj, and then Vj, which cancels. So what you get is that Vj comma V is 0 for all V. Is 0 for all j. But if that is true, right, so this equality comes from the span part, this orthogonality comes from the S part. Right? But now that means that all these guys are 0. But then look at this coefficient, this expression itself. Every single term here is 0. So all of these terms are 0. Therefore, V is 0. And that is what we wanted to prove. Now we have, and so the theorem follows. Okay, so that's the theorem. Now, yeah. 1 second, let me just check. Okay, yeah, great. So that's correct. Okay, so now for the projection theorem or the corollary, which is actually just a corollary of this. So this is getting pretty good. Oh, sorry. Now just before that, let me just start doing the. Oops. Since orthogonality is enough to show. Sorry, what I have to miss is linear. I plan to, just in case of the weather and the clouds and the rain, it interferes, I want to take pictures. It's enough to show. Let me just take a photo. Just going to be the better throughout. Oh, 1 second. Aha, this is better. Okay, good. This is not good. Okay. Sorry, I forgot to do that. So I'm just doing this. Hopefully, this is not needed, but okay. Okay, great. So now, now I can erase this thing. So here is the. So we just. So now let me write down the projection theorem. I can see this on this one. Okay. Maybe I'll call it a projection lemma or something. It's fairly strict. Well, theorem. Yeah, sure, why not call it projection theorem? Because it has 4 parts. It's like a big theorem, long theorem. Okay, so again, V is an inner product space, and S is any subset like here, such that the span is finite dimensional. So why was it finite dimensional necessary? Because at the beginning of the proof, we said something about the Gram-Schmidt process, right? The Gram-Schmidt theorem holds, and the Gram-Schmidt we proved only for finitely many vectors, finite dimensionality. That's why we needed finite dimensional there. Okay, so the same thing here. Yeah, so say S is contained in V and the inner product, just like last time, just like always, is such that the span of S is finite dimensional. As usual, F is R or C, the real numbers or the complex numbers. Okay, then you can write down something. Fix an orthogonal basis. So because it's finite dimensional, I can take an orthogonal basis of it, meaning I start with any basis and then do Gram-Schmidt. Fix an orthogonal basis. V1, V2, Vk of the span and now I define my projection operator. Define. So PS of, let's say any, sorry, define PS from V to span of S. Or V to V, you can even define V to V, V. PS of V is defined to be exactly that thing there, that. Vi, comma V over Vi, comma Vi, Vi. Okay. Now here are the 4 properties. A. I'll call them ABCD. So this is just a map. Or I could even say I can even put in a V here. It doesn't matter. For now, I'm just saying it's a map. But now the flavor PS is a linear map. Is a linear map. From V, of course, to the span of S, but it is subjective. It is onto the span of S. That's the first part. The second is what it does on the rest of the yeah. So if you look at what PS does on the span of S, so look at V. If V is a linear combination of elements of S, then PS of V is V. So if you restrict PS of V to the span of S, span of S, this should be F here, not P. Then what happens? Oh, sorry. If you restrict it to this, then this is equal to the identity. This is not the identity. Yeah, it's the identity map. That's right. Identity map on span of S. And if you restrict PS of to the S perp, oops, yes, that's correct. Yes, so PS of restricted to S perp. Suppose my vector V was in S perp, and this is the zero linear transform. So it's literally the identity transformation and the zero transformation. And since the span of S is finite dimensional, therefore I can take any basis of the S-perp, add the finite basis of span of S. I can write down PS in sort of a matrix kind of notation, and then it's just a block diagonal thing where finitely many things are ones and everything else is zero. That's called the projection operator. Okay, so that's the second part. So in particular, this is all part of part B. If you look at the square of PS, this turns out to be equal to PS as linear maps. As linear maps from B to B. Okay, that is part 2. What is part 3? Part 3 is that this PS of, so start with any vector V, look at PS of V. So clearly, as I said, there is some span of S, right? So there is some, this is the span of S. Okay, and then this is S-perp. And this is the origin. Now take any vector, so this is S-perp. Now take any vector V and look at PS of V. Turns out PS of V is basically its shadow. Like if you take any vector V like this, then PS of V is exactly the shadow. Such that this is perpendicular. So it's the unique point in the plane, in the span of S, which is the closest, it has the smallest distance. And if you take any other point, then the distance to here is this right triangle, is the hypotenuse. So it's clearly bigger than the altitude. The altitude is the closest distance, and that is exactly at PS of V. That is the point of this projection operator. It is the closest point in the span of S, and it's the unique such closest point. So for all V, PS of V is the unique point in the span of S that is closest to S. To V, sorry. It's not closest to S. It is already in the span of S. It's closest to V. Closest meaning the norm is minimized. In other words, I'll just say that. Or the best, which is the best approximation of, another way to informally say it, is the best approximation of V in span of S. What does that mean? So more precisely, in other words, i.e., if you look at the distance from V to PS of V, this is strictly less than V minus S, sorry, let's not say S, let's say W. For all W in span of S, obviously except PS of V. PS of V itself is in span of S. So for all points that are not that unique point, for every other point, the distance from V to W is strictly larger than this. It's a strictly smallest distance. And that brings me to the last part. And the last part is the following. Look at this definition here. This is one property of the vector PS of V. Look at the definition of PS of V. Here, this definition clearly depends on the basis VI. But this is a very unique definition. There's a unique point closest. That is a very powerful statement. In particular, it says that that point PS of V is uniquely identified by that condition. So it doesn't, although it seems to be defined using the VI, it actually isn't. That's property 4. In particular, PS of V does not depend on the basis Vi. Okay, so now let us prove this. This is the picture that I wanted to show you. Okay, so I think we can start to prove the projection theorem. Or do I want to say, maybe I think I want to say something. I want to give you a definition first. How? Well, remark the definition. Remark. This result, this thing about the best fit, the best approximation, is the basis of the most fundamental sort of prediction procedure, the very first one that you learn in statistics, called simple linear regression. So this is the method of least squares. Least squares refers to the fact that, again, instead of looking at an inequality involving norms, you can square both sides and say it's an inequality involving norm square. And the norm square of hypotenuse by Pythagoras theorem is the sum of the squares of the individual coordinates. So that's the method of least sum of squares or least squares. Okay, so this forms the basis of linear regression in statistics. This result forms the basis of linear regression in statistics, or line of best fit, or you may have seen the term line of best fit, or method of least squares. Okay, this is one remark, and the definition I want to make. The definition is very simple. We define PS of V, or PS to be the projection operator. PS is called orthogonal projection. Orthogonal projection of V onto the span of S. So that is the theorem. Okay, now so we just have to verify all these things. The point is, this is very nice. Once you can prove, so you assume that this is the definition, and from that you prove this, then part D is immediate from part C. So there's nothing to prove there. Okay? And now part A and part B, and so A through C are what we have to prove. First, let me just be safe, take a picture. From behind here. It's more convenient. Yes. No. It is, so late in the course, I don't want to risk these kind of things as the problem. Okay, great. So yeah, so let's start with, okay, linearity as always, I will just, linearity as always, I will not prove, I will ask you guys to prove. So, okay, now clearly from V, it's clearly going to span of S. The question is, why is it onto? Okay, well, onto, I will, onto part I'm going to prove, but how do I prove it? Well, from here, let's look at this part here. What does onto mean? It means that if you take any vector in the span of S, it should be equal to PS of something. Well, because of this lemma, it is equal to PS of itself, right? Because V, if you take V in span of S, an identity applied to V is V. Therefore, PS applied to V is also V. So the onto part follows from part B. So part A is really a special case of part B. So let me start from that. Let me start by writing this out. Okay. Proof. Okay, first of all, D follows from C. Okay, so I'm not going to prove D. Okay, so now for A, PS is linear, I will leave to you guys to check. Okay, PS goes from V to span of S, that is obvious. Because of the formula, these are elements of S, so it goes to the span of S. The question is why is it onto? So, and by V, if V is in span of S, then V equals PS of V, because V, it's just the identity, right? And this is so on. Therefore, you're done. Okay, now let me erase this formula. Okay, so that's so. So basically, once you prove B and C, then you're done. So let's start with B and then prove C. Of course, they will not assume part A. So now the claim is that PS is the identity on span of S, and PS is 0 on this thing, and then the square. Okay, let's start with that. What is going on here? Okay, let's start this thing or something. No. Part C was the part C is the uniqueness. I just need to do that for part C. These are all the words. That is the precise mathematical statement that we will do. Okay, so let's do part B. Why is part B true? Okay, so why is part B true? Okay, so why is it so? Let's see. So, let me prove the S-perp part first. That's very easy. So if V belongs to S-perp, we want to prove PS of V is 0. Okay. Then PS of V, what is this? This is summation I goes from 1 to K, Vi, comma V. Vi is in S, V is in S-perp. So what does that equal? Sorry, Vi is in the span of S, V is, is an S-perp, and then times Vi. But this exactly is always 0 because these are orthogonal, and so you're done. Okay, if instead now PS is a linear map. I want to show that anything V, if you take V in V, PS V in the span of S, then PS of V should be equal to V. Right? But PS is a linear map. So if I can show the same thing is true for a basis of that subspace of the span of S, then I know that it is true for every linear combination of that basis, and therefore by linearity, and therefore it's true for all of span of S or for all V. So it's enough to show. So to show that, to show the other part, it suffices to show it for all the V's. To show PS of V equals V for all V in span of S by the linearity of P, which is you have to check. Enough to check for V equals Vi. Enough to check this for V equals Vi. And now let's write. Now let's compute it. So what is PS of Vj as usual? Am I going to do this a third time? No. Check that PS of Vj equals exactly Vj. Actually, we already did this. Check for yourself that PS of Vj Vj for J. Therefore, we are done. So that's part B. Well, that's most of part B. And now we have to prove that. PS square equals PS on the entire vector space. Okay. So finally, so because we proved the previous proposition, take any vector, it can be decomposed as something in the span of S or something in S perp. So if V is V, write V in V as Vs plus V perp by the previous proposition. Where what of course we know Vs in span of S. And V perp is in S perp. So write it this way. And now just check. Now we will check that PS square of Vs plus V perp equals PS of Vs plus V perp. Okay? Let's evaluate both sides, left hand side, right hand side, on this expression and check that we get equal. So what is PS first of all? PS of V equals PS of Vs plus V perp. Because PS is linear, it is PS of Vs plus PS of V perp. But now V perp is an S perp, so of course we know that then that is 0. Okay. I could even use V perp here if you want. So that part is 0. This is 0. And what is PS of Vs? And this part we already said. PS of Vs, anything in the span of S, PS is identity. So this is just Vs. Vs plus 0, which is Vs. Okay, now what is PS square of V? This is PS of V. PS of V is Vs, so it's PS of Vs. But once again, Vs is in the span of S. So PS acts by the identity of that. And so we are not. Clearly, the left hand side and the right hand side are equal to Vs. Okay, now for the closest thing. You want to say that this is the best fit, this is the best approximation of V in the span of S for any vector. Okay, let's do this. So, part C. Yeah. So I will prove the more precise statements. I will take W to be in the span of S, but not equal to PS of V. So say W. And W is not equal to PS of V. So I mean, again, the question already says that start with the V. So we have started with this fixed. Okay. Now then, first of all, because W is in the span of S, so PS of V minus W this is all in the span of S, because the span of S is a subspace, the PS of V is in the span of S, both vectors, and therefore the difference are here. And this is perpendicular to V minus PS of V. Because that's what we just saw in the previous proposition, right? By the previous proposition, V equals that best fitting vector plus the difference, and the difference is in S perp. The best fit vector PS of V is in span of S. So, of course, anything in S perp is perpendicular to anything in the span of S, and therefore that's the perpendicularity. But because these two vectors are perpendicular, I can now use Pythagoras theorem. Right? So let me start with that. So first of all, so I can say V minus PS of V. Remember, I want to show that this is strictly less than V minus W square. That is what we are showing. Let's start with this. Now, because this guy here is not these two are not equal. This is this thing, and it is not the zero vector. So first of all, this is less equals addition of this plus PS of V minus W, norm square, right? Because any norm square is non-negative integer, non-negative real number. So if you take anything and add a non-negative real number to it, it's bigger equals the previous expression. But moreover, because this is not the zero vector, this real number is strictly positive. The vector is non-zero, so its norm square is strictly positive by the properties of inner product space. And therefore, this inequality is strict. So there's my strict inequality. And now I'm just going to prove that this is equal to this. So now here I see that these two vectors are perpendicular. So the Pythagoras theorem what is the sum of squares of these sides? It is the square of the hypotenuse. It's V minus Ps of V plus Ps of V minus W norm square. But that is exactly V minus W square. And so, as I said, this proves part C. Part B was done. Part B implies part A, and part C implies part B. And so this ends the proof of the projection theorem, I think. Yeah. Okay. The next result, so that's the projection theorem. It's a very nice result. The next result is called Bessel's inequality. Yeah. So there are two parts to it. I don't think this is finite dimensional, so yeah. So Bessel's inequality. Bessel's inequality or theorem. Okay. The results is the following. Suppose V is a vector space, inner product space, containing finitely many orthogonal vectors. So suppose V1, V2, Vk orthogonal in V and the inner product. So suppose V1, V2, Vk are orthogonal in the vector space. I think that's the only assumption. One, so there are two parts. For all vectors V in V, if you look at the norm square of V, yeah, that's Bessel's inequality. Then this is bigger equals that thing, that kind of a norm. So it's just literally Vi comma V square. I think this should be mod square, huh? Yes. Divided by Vi square. Okay. Notice if you have this k equals 1 here, then that's the Cauchy-Schwarz inequality. I'll say that. Okay. But anyway. And now this is an inequality always. So when is it that you? So sometimes it will be an equality. For example, if V is 0, then this side is 0 and that side is 0. So of course it's an equality. But the question is, when is it the case that this is an equality for every vector? The above is an equality for all V. This statement is equivalent to saying that the V1, V2, Vk you had form an orthogonal basis. In particular, it means that V is finite dimensional. I had never assumed that. Notice that in this Bessel's inequality or theorem, I never assumed that V is finite dimensional. But that is the point. If you have to have that this is an equality, if this inequality is always to be an equality for every vector V, then the vector space is finite dimensional and these guys actually form the full basis. They're not just some linearly independent set, but they are full basis. I should have said, probably I should have said 0 not equals. Yeah, better to do non-zero and orthogonal. So let's say 0 not equals. Somewhere here. Maybe I have to say it slightly better. Suppose these are non-zero and orthogonal vectors. And again, let me take a picture just to be safe. Okay. So let's prove Bessel's inequality, and then I think after that we are ready to start on adjoints. Yes. Oh, very good. So let's continue. Bessel's inequality. Okay. So first of all, this is not that hard. So basically what we do is the following. We just prove the projection theorem, right? So let W be the span of these VIs. So A, this pen is not very good. Maybe I can try some blue for change. Okay. Now because W is the span of VI, so what do we know? We know what is PW of V, and we know then PW of V equals exactly, well, we have seen this formula by now, you guys are probably sick of it. VI, comma V by VI. Again, I can do this because the VI's are non-zero somewhere here. This. And what is V squared? So V equals, let's see, so V minus PW of V. This is in W-perp plus PW of V. This is in W. So by Pythagoras theorem, because these two vectors are perpendicular, the norm square of V is this square plus that square, which is bigger equals the norm square of PW. So implies by Pythagoras. Okay, so by Pythagoras theorem, the norm square of V it is this vector square, norm square plus this square, and any norm square is bigger equals 0. So this is bigger equals 0. Oops. P W of V square. So norm square. How much is this PW? But PW is the sum of these guys, and these guys are orthogonal. So again by Pythagoras theorem, I can say that this norm square is equal to Vi comma V square by Vi comma Vi square. And then the norm square of this guy. But the point is, it is the sum of squares of these vectors, which is perpendicular. So it is the sum of squares of this norm. But the norm square, the scalar comes out. So this is the scalar coming out, and then this is norm square of Vi. I goes from 1 to k. But now you see, this is exactly norm square of Vi, and there are two of those. So I can cancel one of them with the entire norm square. And so I get exactly that. I get Vi comma V mod square divided by Vi, but Vi is a non-negative number, so I don't need to put the absolute values, and Vi is exactly norm square Vi. And I think that is exactly what Bessel's inequality was saying. The norm square of V is bigger than this expression. So it's just a matter of writing it out and doing the calculations. But yeah, it's basically just Pythagoras theorem, that's all it's saying. Okay, so now the next thing I want to do is proof part 2. I'm going to prove part 2 as a series of if and only ifs. The first thing happens if and only, the second thing happens if and only. And eventually we will get to the conclusion that it's an orthogonal basis, orthogonal basis. This is part 1, not 8. Okay, so this is an equality for everything. So this. So when this is an equality, so what was the point? This inequality was because I was using that V minus PWV. Norm square is bigger equals 0. So if I want, there is no other inequality here. So if I want this to be an equality, this had better be an equality for all V. So equality. By the way, yeah, fine. Equality for all V is the same as saying that V minus PW of V norm square is equal to 0 for all V in V. But what does that mean? When can a norm square be 0? The norm square is 0 if and only the vector is 0. The vector is 0 if and only V equals PW. For all V. But look, W is a finite dimension. These are finitely many vectors, so W is finite dimensional. How can PW? Now we know what projection operators are. Maybe I should have said that. This is finite dimensional. So, because it's finite dimensional, you can define the projection operator. Okay, but now what happens? How can a vector be equal to its projection? What we proved in the projection theorem was what happens if you take the W-perp part. On W-perp, it must be 0, right? But how so? But this means including on W-perp. Okay, now if W equals V, what is W? W is the span of these guys. If W equals all of V, then this is obvious. Because the projection is the identity vector on the span, which is all of V. Right? So if W equals V, so maybe I'll do both implications separately. If W equals V, then this follows, then V equals PV of V is identity because of the projection theorem. Equals PW of V. So that is fine. Conversely, if V equals PW of V, for all V, and let me just say for all V in W-perp. But on the other hand, what is PW of anything in W-perp? It is 0. Then what we get is, then V equals PW of V in V-perp, but that is equal to the 0 vector. So what do I want to prove? I want to prove that if W is V, then this happens. Let me just show. Conversely, if this happens for all vectors V, then V equals W. The W is the span. Well, that is because now anything in W-perp must be the 0 vector. So which is a vector subspace with whose perp space is 0? That is exactly yeah. Right? Or you can even do the following. Maybe I can say, well, now take any So this means W-perp is 0, right? So this means W-perp is 0. But every vector is the sum of something in W plus something in W-perp. And W-perp is 0. Therefore, that vector, the something in W must cover every vector. So W equals 0. The moment W-perp is 0, this implies W equals 0. Okay, that is the next statement. That is the proof of Bessel's theorem or Bessel's inequality. And now I think we can finally start on adjoints. Okay, so let's start on adjoints. Yeah, we have half an hour, so yeah, should be enough to do some of this part. Okay. Some water. Okay. Adjoint linear. So let me call the title adjoint. Okay, and maybe I should clarify here. The adjoint is not the transpose. So the point is that we have used the transpose was sort of defined for every single vector space over any field, not just R or C. The adjoint is defined only with respect to an inner product space. Give me a map on V comma. The point is that here now we have to use the inner product. Yes, that is the okay. And so the way it's defined and so on is through a theorem or a proposition. So let's call it a proposition. Suppose it's so, and now I will actually use the adjoint of a matrix. So basically, I'll use the adjoint of a linear operator on a finite dimensional inner product space. So now we will stop using infinite dimensional. Basically, I think for the rest of the course, well, sort of. Okay? Some vague things we will say are also true when it's infinite dimensional. But really, we'll just use it for finite dimensional inner product spaces from now on. So proposition, let me, how many pages do I have left? 1, 2, 3, 4, 5, 6. Oh, wow. Today's okay. There are still 2 more lectures. That explains it. Fine. Okay. So say V is finite dimensional. What's the point of this? Again, and of course, the ground field is either real numbers or complex numbers. So the finite dimensional, and T is in linear. T is a linear map. Right? So of course that is as usual. Now there are 3 parts. First, for any linear map, I can basically define T star, the adjoint. Okay? So there exists a unique linear map. Also belongs to lin VB. Such that this TV comma W, or which way I want V comma W, such that V, if you take V comma TW, this is the same as T star V comma W for all V and W in V. Okay? Just that one condition, and that is enough to uniquely define a different linear map related to T. Now, how are we going to prove this is very interesting. We're not going to prove this directly. Okay, okay, first of all, I'll say this is if and only if this equality. This second part is trivial. This equality is if and only if I can do the other way. Of course, why should I do v comma tw? Why not tv comma w? So sure, tv comma w is v comma t star for all v w. Okay, so this part is easy. To prove that these are equivalent is sort of trivial because the inner product satisfies these nice conjugate properties. The hard part is the other one. The hard part is the first one, that there exists such a map. And that is done using this part. And this part has nothing to do with T at all. This is to do only with the inner product space. So the map, and it has to do with a very different map. I will call it capital phi, from V to V star to the dual space. So even to understand, what do you call this? Adjoint matrices, meaning conjugate transpose matrices, the proof actually uses dual spaces. So it's very interesting that, we define the dual space just as an object of sort of intrinsic interest and so on. But it really is useful in terms of defining the adjoint, meaning the conjugate transpose. To prove some things like this, you need the conjugate transpose, you need to use the dual space. Once you define and prove this theorem, then we can go on to the spectral theorem. That's really where we are going. But first of all, today I guess I want to just prove this theorem. Tomorrow, next class, we will look at the basic properties of adjoints. That's not very hard. And some things about orthogonal maps, of course, orthogonal maps, because you need them to understand the spectral theorem. And then we will do the spectral theorem. And if I can, I'll prove it next class itself, but my guess is that I probably can't. We will see. Okay, so for now, let us continue. So I want to get to this point, and then 1, 2, 3. And then okay, very good. Yeah, we will need 2 more classes. Not one. I was thinking we might, but no, we will need both classes. Okay, so very good. So this map phi sending. What does this map do? It's very simple. It sends v naught. I want a linear function, right? So I should take consider the following map: v naught comma dot. So this is a map that takes a vector v to the inner product this thing. So phi of v naught is a map taking v to the inner product of v naught. This is a linear isomorphism. So that's actually not quite true. It's a conjugate linear isomorphism. Is a conjugate linear isomorphism. Okay. Conjugate linear just means that phi of c v naught equals c bar times phi of v naught. And that is actually obvious. You can just verify it here. C v naught inside here, the c comes out as c bar. That is it. But that's what conjugate linear means. It means that this, when the scalar comes out, it's not c but c bar. Okay. And it's a conjugate linear isomorphism from v to v star. So v is conjugate linearity isomorphic. Okay, great. So that's what we want to prove. Definition: such a map, this unique map that exists, is called the adjoint of T. And this is sort of explaining why earlier we called that map the transpose, even if that was denoted by the star as well. That was slightly different. It's a transpose map was different than the adjoint. Okay, again, I need to take a photo. We have about 20 minutes. That should be enough to prove. Okay. So again, let's erase. This proof is slightly longer, so now this time it won't. That proof window that kept intact will no longer stay intact. Okay, so that's it. We'll prove part 2 first, then part 3, and then part 1. I think that's right. Yeah. Okay, the part 2 is just trivial, so let's do this. So part 2. Which way do I want to prove it? Let's do it one way or the other. So, suppose 1 holds, I'll prove. So, okay, we want to prove 1 if and only if 2, right? So, let's see 1 implies 2, and 2 implies 1 is similar, so that's fine. So, now let's start with the left hand side, TV, W. Well, but that is the same as by the axioms of the inner product, not of these things, but of the inner product. I can solve those. W, TV, bar. But now if I have W, TV, then that is the same as P star W, V. With that, I keep the bar because the bar is there, conjugate. And now I can again flip back using the inner product axioms. So that is what we want to do. And you can imagine that 2 implies 1 is very similar, so I will not work it out. You can, and it's basically trivial. Now let's prove 3. 3 is the main thing. Once you have 3, then 1 is not that hard. So let's do a bunch of different things. You have to do all the book. Basically, this is called bookkeeping exercises. You have to verify that every single axiom or property holds. So the first question is this map going to V star? Is this linear? You have to check it's linear. It's not immediate or something. Is it linear? Well, yes, it is, because it's linear in the second coordinate. That's why we kept the second coordinate 3. Okay, let's start verifying. So A, phi of V naught belongs to V star for all V naught. Okay, so this is the first thing to verify. So well, let's look at phi of V naught of CV plus W. Right? You have to verify something is linear. You have to check that that map applied to CV plus W is C times the map of V plus the map of W. Let's check. This is equal to V naught, comma CV plus W. But now we know this thing, right? We know this is V naught CV plus V naught W. And also V naught, comma CV, it's linear in the second argument, so C comes up. I'm just going to skip one step. And say that it is C times V naught B plus V naught W. Okay? But then what are these things? This is exactly C times phi V naught of V plus phi V naught of W, and therefore, yes, it is linear. Okay, part B. After that, it's linear. So indeed, phi does send V to V star. Secondly, is phi conjugate linear? Yes. Oh, so first of all, phi, all we have said so far is phi is a function. Now we want to say phi is conjugate linear, so phi is additive. This is again obvious. So if I take phi of V naught plus V1, apply it to any vector V, well then this is exactly V naught. Sorry, 1 second. 1 second. It's strange, and my phone never used to work, and suddenly it's activated. Maybe it's a horror movie that I'm living in. We will see. If it is, then you're in for some interesting time in this video. But somehow I doubt it. Okay, so yeah, so but what is phi V naught of V1 plus phi V naught plus V1 of V? This is literally V0 plus V1 inner product V. That is all. And that is obviously V0 V plus V1 V because it's additive. As you can check that this is indeed phi V0 of V plus phi V1 of V. But now what is the point? The point is as this happens, so here is the map, here is the map, and here is the map. And we are saying that this map equal of V equals T of V plus T2 of V, or T0 of V plus T1 of V. But that means that as if these two are evaluated every point V to be equal, then that means that the maps themselves are equal. Phi of V0 plus V1 as a map inside this linear space V star. So like both sides are maps. So okay, let me not write the equality first. Consider these two maps, right? This belongs to V star, and these two maps belong to V star. Therefore, the sum belongs to V star because V star you can add and subtract and so on, right? And you see that when you what are maps in V star? What are elements of V star? They are functions from V to the scalars. So if you evaluated every point V, the left hand side and the right hand side, you get that they are equal. Therefore, the functions are equal. When two functions agree at every point, they are equal. That's all we are saying, right? Okay, so that is the second bookkeeping. Phi is additive. Now I can say phi is conjugate linear. This is just obvious. Now, what does this mean? Already I have proved it's additive. So the only conjugate linear extra part is to prove this. But this is just obvious. Evaluate both sides at any vector V. You get CV naught inner product V equals C bar V naught inner product V. So again, both sides are elements of V star because you can scalar multiply in V star. And they are both agreeing at every point V. So I won't write this down. I'll just say it follows from star. Follows from star. Okay, so I've proved all these things. Let me also show you one-to-one and then onto. Is there anything else there? No, that's it. Sorry. The onto part is the hard part. So the one-to-one part, maybe I'll do it here. V phi is one-to-one. Okay, and for one-to-one, again, it's enough to show that the kernel is 0. Why? Because I sort of, I didn't lie, but I sort of overstated things. We said that if a linear map is one-to-one if and only if its kernel is 0. But in fact, it's enough to do this for an additive map. I don't even need the scaling part. Even if it's conjugate linear, it's one-to-one if and only if the kernel is 0. Try to check it for yourselves. I won't. Okay. So say phi of V0 is 0 is the 0 linear transformation, 0 in the V star. Okay. Then if you evaluate V0, what does that mean? It means that it's 0. It means that V0, comma V, all the vector spaces is identically 0. Is 0, is scalar 0. But then there was a homework problem. Homework problem said if V0 is orthogonal to all of V, then V0 is 0. I mean, it's a trivial homework problem. It's like half a line, not even one line. But whatever. But that's exactly what one-to-one says. If you map to 0, then you must be 0. Great. So that is one-to-one. Okay, now finally, so we want to prove, remember, we are proving, the only thing we may need to prove is that phi is onto. So let me start with that. And then let me take stock of what we are doing, okay, what we have left to do. Okay, so part E is phi is onto. Okay, so once I prove phi is onto, then I would have finished the proof of part 3. The map phi sending V to V star, it does send things to V star, is conjugate linear and an isomorphism. It's a conjugate linear isomorphism. So it's also bijection. So that's we would have finished this part 3. We already saw why part 2 is the same as part 1, and then we will end up proving part 1 and finish the lecture. Okay. Yes. Okay, so let's do this. Is this also? Okay, so y is phi on 2. We know that the vector space is finite dimension. That is going to be very useful. And again, what we are going to do is, so far, you see, I've just written inner products and this and that. But now we will actually use the fact that a finite dimensional vector space has a basis, part 1. And then secondly, from Gram-Schmidt, you can convert that basis to an orthogonal basis. And so that's what we are going to use. And then we'll do projections and stuff like that. Okay? And so this is why we need finite dimensional. So, okay. What do we want to show? We want to show phi is onto, meaning any element, any linear functional is exactly equal to the inner product against some V naught. So given the linear functional, I want to find V naught. So the way to do it is to start with the orthogonal basis, and then from that we will figure out the V naught. So this is really the key. So V is finite dimensional implies by class and Gram, like very early in class, plus Gram-Schmidt. I'm just skipping the step basically. I should have said there exists a basis and then the Gram-Schmidt I'll make it orthogonal. But I'll just say, let me make it orthogonal to start with. There exists an orthogonal basis. Do I want to call it V1 to Vk or V1 to Vn? Apparently still. Let's even make it order just to be happy. So everybody is on the same page. Orthogonal order basis. Okay, so I have this nice basis. Fine, great. Now what do I do? Now, okay. So now I need to prove this thing. So now given I want to show that phi, any element of V star, any function, is something like this. It is the inner product against. You claim that phi. Phi is phi of V naught, where V naught equals summation I goes from 1 to k. And now here I need to write down something about phi of Vi, I guess. Phi of Vi bar over the, I guess, norm square of Vi. Yeah. So, of course, then because the V1, V2, Vk form a basis, whatever V naught I take is in the vector space, and therefore it's a linear combination. And I'm telling you that these are the unique coefficients. In other words, that is to say, we want to prove to show that phi of V naught, phi of any vector V, is equal to summation, is the inner product against this guy. So it is I equals 1 to k, phi of Vi bar divided by is the inner product of this thing by norm square Vi and V. Technically, I can even put the inner product outside the summation because that's really what it's saying. Phi of V is the inner product of this big vector and V. That's what we want to show. Okay, let's calculate. So compute. Yeah, so we have to just compute this. Sorry. We are claiming this. Again, I will do the same strange thing. Proof. Look at the left hand side here and the right hand side here. So phi of V versus V non bracket V. Right? This is left hand side, this is right hand side. I want to show they are both equal. What do I know? I know that phi by definition is linear. And this by definition is also linear. It's linear in the second coordinate. Since both sides are linear, to show that something they agree at every single vector V, it is enough to show that they agree at a basis. And so I will again just evaluate at the basis Vj. Okay. Since LHS and RHS are linear, now here they are not conjugate linear, they are actually linear. In V, enough to show they agree at V at a basis, agree on a basis. And of course, we just have one basis we have chosen. At all vectors Vj. That is what we will do. So check. LHS and those. Let's start with RHS at Vj. What is RHS at Vj? It is summation I equals, okay, because inner products are additive in both arguments, I can take the summation and inner product switching. So I get phi of Vi bar over mod Vi norm square, and then Vi and Vj. Now the scalar will come out, but yeah. Maybe I should make the scalar come out. And I don't need it, right? So you can imagine the scalar comes out, you get Vi bracket Vj. But Vi bracket Vj is always 0, except when I equals j, because they are orthogonal bases. And so this is summation. There is no summation now, so the summation goes away. This is the inner product of phi of Vj, now I equals j bar over norm square Vj. Okay, Vj. And now look, so first of all, because this comes out, I have to take the conjugate of this. And what is the conjugate of this? It is the conjugate of the conjugate of phi of Vj. So this is the cleverness in putting the conjugate here inside. Because it's in the first argument, when you take the scalar outside, it will get conjugated. So you get phi of Vj times, and of course this divided by the denominator, the norm square, and then you get Vj. But Vj is again norm square, so that cancels with the norm square in the denominator. I'm skipping a step here, if you will, but that's it. And so the right hand side at Vj equals phi of Vj, and that is exactly the left hand side of Vj. And that finishes the proof of part 3. Okay, because now it is indeed onto. Phi is exactly equal to evaluation against this vector. Okay, so again I have to take a photo. But now we are almost there. Now I will do part 1, and we prove part 1 of the what is this theorem called? Of the adjoints existence, basically, and then we will stop. Okay, great. The last effort is to prove part 1. Okay. Now it's even better. Not just the proof remains, but part 1 also remains. Okay, fine. So far what we have done is so we have not said anything about the linear transformation T in all of this part. Now we will use the transformation T. Use this extra fact about the inner product, every linear functional looks like something, and using that we will define T star. Okay, and then prove that it's linear and some nice things happen. Okay. So one does not only uses 3. So we said that 1 was different only if 2, but the point is, basically the idea is first prove part 3, then prove part 1 which only uses 3, and then do that silly equivalence which is just very, very tricky. Okay? So yeah. So now here is the one. Given, let's look at the following. Given any vector V0, the definition of T star is going to be very indirect. So it's a very sort of tricky definition. So given V0 is B, I'm going to consider the composite map as follows. Okay, so I want to define the map in V star. So state, okay. So fix a vector V0, the composite map in V star from V to F. How does it do? It takes a vector V here, and I will tell you what to do to V. This one is fixed for me. This is the test vector. Sending. Start with the vector V in V. Then apply the map T. So you get TV, which is still in V. And now I apply the map to F, which is exactly the inner product with V. So this is clearly a linear map because it is a composite of two linear maps. Okay. Is a linear functional. But once it's a linear functional, what was part 3 saying? Part 3 was saying any linear functional is exactly phi of something. So now I've already called it V0. So hence by part 3 it equals, let's say, phi of V0 tilde. For some, but in fact for a unique, one-to-one part, right? It's for a unique phi V0 tilde. So given any vector V0, I got a unique vector V0 tilde, and that is what I will define to be T star of V0. Define T star from V to V via this. T star V0 is V0 tilde. This is a unique definition. There is no ambiguity. There is no question that the definition cannot happen. There are two possible answers. No, this is well defined. There exists and unique. Okay, so that's what it is. That is my definition of the map T star. All we need to verify. Remember, we just need to verify that T star is, what do you call it? First of all, it's there exists a unique linear map that satisfies that inner product condition. So we need to verify there exists is fine. And let's see. What about uniqueness? I don't think I'll verify uniqueness. The uniqueness is because you can just let's see. Okay. So first of all, yeah, so therefore some T star, okay? Now let's check these things. So then T star is well defined because of all these things. The second is that I need to verify this T star V comma W. Let's look at T star of V0 comma W. Okay. But T star of V0 comma W is V0 tilde comma W. Basically, we are saying, see, we never had any restriction on V0 either. So start with any V0, start with any W. Look at T star of V0 comma W, which is V0 tilde comma W. But V0 tilde comma W is what? It is phi of V0 tilde of W. Phi of V0 tilde applied to W. And now what we know? We know that phi is exactly this composite map. So therefore, phi of V0 comma W is V0 comma TW. That's exactly the composite map. And therefore, this is what we wanted to prove anyways. So we are done. So yes, T star exactly satisfies this by the definition. So it works out pretty well. So now the remaining part is that it's linear and it's unique. Okay, so let's continue. Okay. It's linear, it's unique. So it's nice and linear. T star of CV plus W. Let's call it CV naught plus W naught, just to be safe. So how do you check whether it's linear? So why is this equal to something? Right? So you want to check that this is linear. The way to do it is the following. Take any. So let V naught, W naught, and V belongs to V. Now evaluate this. So what we know is that right. So it's this now again by the same kind of trick. We know that this equals now I can use B. So by B, this is equal to CV naught plus W naught TV. But this is CV naught comma TV plus W naught comma TV. And now, of course, remember the C comes outside as a bar. But now what is V naught comma T? Okay, let's write this down carefully. Still. So far I've done nothing except bring out the C as a bar. But now you see that V naught comma TV, again I can use T star. So C bar, T star of V naught, comma V, plus T star of W naught, comma V. And now I put back the C bar inside the inner product. So it is C times T star of V naught, comma V, plus T star of W naught, comma V. And now I can again combine because of additivity. Great. So I started with something, comma V, and I got to something else, comma V. Well, the obvious expected something else. It's not like some state. So when I subtract, let's subtract. I think that's it. I should not have to use my homework twice. No, I don't. I hope not. Yeah. Anyway, and so this is true, as I said, for all V in V. What does this mean? Subtracting, which is, so this is subtracting. Basically, left hand side minus right hand side. What do we get? We conclude that minus this. So T star C V naught plus W naught minus C times T star V naught plus T star W naught, comma V. This entire big vector, right? These are all vectors. T star is a linear map, so T star of this is in V. This is C times the vector in V plus something in V. All of this is a vector in V. And of course, this is in V. And we are saying this vector, whatever this is orthogonal to everything. So I can just say this is orthogonal to all of V. That's what these things are saying. That minus that is 0. By the homework problem, which is the only vector which is orthogonal to all of V, it is 0 itself. Implies this guy is 0. So I don't say a priori I want to show something is equal to something else as vectors, but in an inner product space, you can show that two vectors agree if and only if their difference is perpendicular to the entire vector space. So that's how we are doing it, slightly indirect, but it's nice. And so this is 0, and therefore, so what we get is without the v, this minus this equals 0, so this equals this, and so t star is 0. As I said, I want to show that it's unique as well, but basically, yeah, you can check this, right? So again, why is it unique? Because uniqueness also follows from this. Suppose I have t star 1 and t star 2 that follow like this. Then check that t star 1 v naught minus t star 2 v naught is killed by all of the w's. And therefore I'm done. Sorry, 1 second. So maybe I will do it here, just to tell you. So implies that this vector, whatever this vector here is, equals 0, implies t star is 0. Okay, and now the last part is to somehow say that it's unique. Okay, so say I have two vectors, t star 1 and t star 2. T star 1 of v naught, comma w equals v naught, comma tw, and t star 2, another different linear map, also equals the same thing. But then what do I get for all v naught and w? Then what do I get? Then I can just subtract this minus this, and I get t star 1 v naught minus t star 2 v naught. Now if I take the inner product against w, I get this minus itself, and that is 0. It is the scalar 0, sorry, not the vector. And this is true for all w. So here is again a vector. T star 1 v naught minus t star 2 v naught is a vector that's perpendicular to all of v. So again, by the homework here. Again, by the same homework problem, this vector must be 0, and therefore t star 1 equals t star 2 at every input. Therefore, those functions are equal. By the homework, t star 1 equals t star 2. Now I can finally stop it, take my photo, and we are done. So next time we will talk about the basic properties of adjoints, then talk about orthogonal maps, unitary maps, and conclude with start the spectral theorem. I mean, mention the spectral theorem, maybe do a little bit of the preliminary result towards its proof, and the final class we will finish the proof, and that's where the course ends. Okay, this is the thing if you want, if the photograph works out. So yeah.